This lesson is on chapter 19, sections 3 and 4, about the moon, the phases of the moon. Before I start on the phases of the moon, I did want to do really quickly a review of the seasons because many people either didn't draw a proper picture in the lab or did not do well on the quiz. So take a quick look at this. Here's the way, and I mentioned it at the beginning of last week, but it probably makes more sense now that you've done the whole week. If you look at a picture like this, you cannot just remember, oh, summer is on the left and winter is on the right. What you have to look at is how directly the sun's rays are hitting the earth. And if you know that, you can figure out everything else. So if you take a look at this picture, and when you draw the pictures, in order to understand where the earth is and which way it's tilted, you need to draw both the equator and the axis of rotation. When I looked at your lab, some of them were very difficult to figure out what your picture was because you had a big tilt, but you didn't, and there was one line. And I had to kind of guess if that was the equator or the axis of rotation. And so what you do, obviously here is your N for north, your S for south. So I know that's the axis of rotation. And then this is the equator. So then what you want to do is you want to look at the rays of the sun. And when you look at the rays of the sun, roughly coming out parallel here, where are they mostly hitting? Towards the south or towards the north in this picture? In this picture, it's clearly hitting the southern hemisphere more directly. And here they're kind of bouncing off at an angle. This is kind of like I like to compare it to in the summer, when the sun is directly overhead between like 11 and 1 o'clock, that's when you get the worst sunburns because the sun is coming down more directly at you. Sunrise and sunset, later in the evening, earlier in the morning, it glances off at an indirect angle. So if you know that, then you're going to say this is summer in the southern hemisphere, which means it must be winter in the north. The other thing you can look at, if you were to draw kind of day-night here, as it's rotating on its axis, which hemisphere is having 24 hours, or which pole is having 24 hours of dark? The North Pole, so it must be winter in the north. So if you know this is winter, then you draw the arrow. If there's not already arrows, if you're not sure which way it's going, draw arrows. Usually, the kind of standard is that counterclockwise. Counterclockwise rotation on the axis, counterclockwise rotation here. So if this is winter in the north, what season must this be? After winter comes spring, then summer, and then fall. And again, if you look at it, double check yourself here. If you look at the picture and logically see what's happening in the picture, you should be able to figure it out. And then you just fill in all the rest of it from there. Question? And here's a simpler picture of the same thing. The question was, would you have health problems living in either 24 hours of light and 24 hours of dark? The major problem actually is it's just kind of weird. So there tends to be, it messes up your sleep cycles. So a lot of times there's depression or anxiety or things like that, but not any, they're more psychological, not physiological. Yeah. Last weekend I posted, I don't know if any of you looked at this, I showed you the one animation for seasons, and then I found this one. And as I said in the post, this one is way cooler. So if you click on this, and take a look at this on your own time, but this, again, I just did a Google search for seasons animations. You do the exact same thing for moon phases animations, but this shows it, so the X that it keeps showing is in the northern hemisphere, kind of roughly where we live. You've got the sunrise, sunset, and it's showing you how high it's rising. So there's a lot of interesting things here. And then you can change things. But anyways, it's just another website that you can check out. So let's go back to the phases of the moon. So what causes the phases of the moon? Again, you read about this yesterday. And here we obviously have And as somebody pointed out yesterday, this is not to scale. The distances are much greater, but then we couldn't fit it all in one picture. But of course, at any given time, we have the daylight side and the nighttime side of the Earth. And so you can easily shade that. This, again, when you are taking a quiz or a test and it's asking about the phases of the moon, the first thing you do is, where's the sun? Here's the sun. Okay? So it's always going to light up the things facing it. It can't, and the other side will be in shadow. So what you could do is for the same, you can do the same thing. It's kind of an odd looking picture, but always half of the moon is lit, right? The side facing the sun is always lit. And what changes is what part of that we can see. So what I do if I'm answering a question like this, I look at it, and the first thing you want to identify is, where's the full moon? Which one's the full moon? The full moon. This is going to be the full moon because as you are standing here on the Earth, and the Earth's, of course, you know, rotating around, oops, what you see here, looking up, is you see the full moon. This is what you see as a full moon. And then what are you going to see over here? Nothing. No moon. No moon is the new moon. Strange name, but that's what it's called. Yes? The sun is so far away that you can, but I mean, there's never going to be between the sun and the moon. I mean, the Earth and, what's he trying to say? Yes. Right. Okay. Okay, so the question is, how can the moon get any light here because it's in the way? So part of it is, remember that it's actually not exactly in line, so it's a little bit above or a little bit below. And also there's a certain amount of the diffraction around the sides. But mostly it's that it's far away and that it is actually above or below. And if it does pass through the shadow of the Earth, then that's an eclipse. And we'll do eclipses here in a minute. So we do this, new moon, full moon. And then again, the names are a little bit confusing to me, but after the new moon, actually let's do the full moon. So if we're going this way, we'll continue our counterclockwise, as I mentioned earlier. After it's full, what's it going to be? A little bit less than full, right? And so imagine it kind of like that, because this part is dark. And it's kind of hard to see on this diagram, but if you imagine, and I have these little cardboard ones you can look at, if you imagine how much you could see, you would see this much. So you see not quite a semicircle. And we call that the gibbous moon. And because it's getting smaller, we call it waning. Like your attention is waning. It's getting smaller. It's dropping off. So that's the waning gibbous. And then when we get to this phase, keeping in mind that what you're going to see is this. So you're seeing half of it. But of course, we don't call it a half moon. We call it a quarter. And I started at the full moon. You should technically start at the new moon. This is the third quarter. We are 3/4 of the way through the moon cycle. We always draw it counterclockwise here. Third quarter. And then here, if you can imagine, what you're going to see is just this little notch here. And so what that's going to look like is just a little crescent. And so that's the waning crescent. And again, logically makes sense. The moon phases are confusing, but all you have to do is figure out full moon, new moon, and then just follow the pattern. Excuse me, you get the new moon where you see nothing at all. And then what's going to come after the new moon? And this should have been first. When you do the moon phases, you start with nothing and then go. A little tiny one. So again, you're going to see a crescent. Yes, and we call it the waxing crescent. How do you remember that? I don't know, but you know, the good old Karate Kid, wax on, wax off. But you have to remember wax on because it's getting bigger. And you remember your attention is waning. People have usually heard that. So, and then you'll get to here. This is actually going to be the first quarter. And then this one again, where you'll see a little bit more than half, is going to be the waxing gibbous. And yes, I will ask you a question on the quiz to label all of this stuff. And I think I have, I'm trying to find the other picture. Oh. Yeah, it looks actually kind of like that. There we go. So you can take, and sometimes I do a worksheet. So it starts out looking like this. Now, immediately as you look at this picture, what one big major thing is different on this picture than it was on the one I just showed you? The sun is on the other side. Okay? So it changes everything. It just makes it all, so sun's rays, the sun's on this side. So, so you do the same thing, but then what this diagram is supposed to be, just like I just drew, this is, and it bothers me that they didn't make a shadow on the earth too, so shadow on the earth. And then what's supposed to be in the outside circles is just showing you what phase it's in. And so that would look like this. So you got the new moon. Is that right? Yep, that's right. So we got the full moon. I know, I don't know what happened to the full moon there. And these numbers have it going around this direction here. And so again, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent, new moon when it's dark. Okay, so logically, you can do that. You figure it out, no problem. Excellent. Okay, so let's move on to eclipses. And again, it's easier to demonstrate, and you can play with it tomorrow in the lab, when you actually have a moon and a sun and some styrofoam balls and an earth. But what's happening is in real life, the moon is slightly above or slightly below the plane, so you're not getting an eclipse every month. But there are two types of eclipses. First, there is a solar eclipse. Right, and you know what? It's just what the name tells you. A solar means the sun, eclipse means to cover it up. So the solar eclipse can only happen in a new moon. The new moon passes between the earth and the sun. Right? So, and the reason you know that is because if you look back at our diagram, when is the only position when the moon could block the sun? Here, right? So eclipses are only going to happen either at the full moon or the new moon. And if you think about your picture, you know where they have to occur. So a solar eclipse happens when the new moon passes between the earth and the sun. These are do not occur very often, and they're seen only by a small portion of the earth. Because as you see in this picture, that again is a little confusing to look at, but when you think about it, because the sun's rays spread out, the shadow of the moon on the earth is just going to be a small dot. And so this is when you hear that a certain part of the United States or a certain part of the world will see a total eclipse of the sun, and others will see a partial eclipse. And one of the things, there was one in the United States just a couple years ago, and part of the problem is if the solar eclipse happens when it's nighttime for us, we're not going to see it because the sun's not out. Yeah, did any of you guys see the solar eclipse? Was it 2 years ago, in the spring? And it was right at, it was really close to sunset, and so it was pretty cool. But it's very rare. In the time I've lived in Colorado, that's the only time there was a total eclipse that was fairly visible here. The lunar eclipses happen fairly often, and I'll show you. You can actually go on the NASA website, or you can just Google or search for it. But scientists, they use crazy math, and they calculate out when exactly they're going to happen and where they can be seen. Now, the lunar eclipses not only happen more often, but anytime there's a lunar eclipse, it's going to be seen by the entire Earth for two reasons. One is because in the time, the way the proportions are, the size of the shadow of the Earth is much bigger than the moon, so it covers the whole moon. And this very red tint is where there's kind of an odd bending of the light, but just before and after the total eclipse, the red wavelengths bend around and the moon turns a really pretty red color. But then you can see it generally over a wider area. You guys ever seen a lunar eclipse? Remind me, and we'll look up when the next eclipses are coming up. Because when you see it on the news, sometimes they tell you, like, you know, a very short advance. Okay. These are going to be tides again. Okay, any other questions about, and of course, the lunar eclipse can only happen during the full moon, because it is only during the full moon that the Earth would come between the Earth and the sun. And normally the moon, rather than being eclipsed every month, is up here or here. And so they have these other words here, umbra and penumbra. Umbra, think of like umbrella. The umbra is the area that's totally covered. So the umbra is this area. The penumbra is in partial shadow. And so that's more pronounced here. The umbra here is that area that's getting the total eclipse. Penumbra is going to be partial eclipse. And again, remember that by the word umbrella. And then penumbra. Okay. Something else, I forgot what it was. The other interesting thing about solar eclipses, the sun is obviously so bright that you can't really look at it. And even with telescopes, it's very difficult to observe the sun. And so it used to be that, and probably still to some extent, when there is a total solar eclipse, it is a unique opportunity for scientists to see the sun in a way we're not usually able to see it. And so in a solar eclipse, as you see here, the total eclipse, you're going to see just this outside part, just the corona. And you can look more directly at it, both with telescopes and, of course, you never look at the sun with just your naked eye. But so you can study, they can study the corona and some of that stuff in much more detail than you can in the regularly looking at the sun. And in a very strange twist of, I don't know, coincidence, the moon is, for the diameter, 30 times smaller, but 30 times closer. And so in this eclipse, they exactly cover each other up, which is, when you think about it, whether you ever realized it or not, the sun and the moon in the sky appear to be the same size, which is very strange, but very cool. Yep. Right. 30 times bigger, 30 times farther away. Yeah, exactly. So it's pretty awesome and pretty randomly strange. All right, everybody got eclipses? Make perfect sense? And in the lab tomorrow again, you'll have a chance to kind of practice that. Yes? So going back to seasons for a moment. But yeah, the further north, even if you're not in the Arctic Circle when you're going to get 24 hours of light, obviously it changes gradually by latitude. So even if you live in Montana, in the summer your days are going to be much longer than they are here. And in the winter they're going to be shorter. Or Canada. So the further north you're going to get that effect. And you really notice it if you ever travel, just, both summer or winter would be the most extremes. Even traveling within the United States, north and south, to either somewhere far north like Washington State or Minnesota, or traveling farther south to southern parts of Texas or Arizona, you're going to see a noticeable difference in the minutes of daylight. Yeah, and but the time zones are east to west, right? And so this is north to south in terms of hours of daylight when the sun sets. In the summer, when does the sun set here? Like 8 o'clock, 8:30. It might be 15 or 20 or half an hour later somewhere else. Um, the apps you have for your phones, the newer weather apps actually have sunrise and sunset on them, so you can kind of look at those if you've seen those. If you have such apps, you should check those out. Um, the newer apps like this, you can see. Oops. Okay, the moons and tides. Again, this is a quick review. We talked about this a couple weeks ago, but I do think now that we've talked about the phases of the moon and that this makes a little bit more sense. I'm not going to go over this in great detail, but do remember the spring tides and the neap tides, the related to gravity. And so, of course, as you see up here, when the sun and the moon are lined up in the same direction, it pulls, gravity pulls on it, and that makes the high tide. When they are perpendicular to each other, they're pulling both opposite directions, and so you have a smaller difference between the high tide and the low tide, and that is called neap tide. So spring tide, springing, jumping, big difference between the two. Neap tide, lesser difference. Okay, there's your. Okay, so a couple of interesting random facts about the moon. One of the things I think is fascinating about the moon, Galileo ends up being one of my favorite scientists because he just discovered everything, right? He discovered the moons of Jupiter, and he actually was one of the first ones to observe our moon in a great amount of detail. If you do not have notes on this already, I would write down notes because there are questions on the quiz about such things. So in 1609, Galileo used a telescope and he looked at the skies a lot. He observed many features. He's the first one who saw the Maria, the flat areas. He thought they looked like oceans, so he called them Maria, which means oceans. He saw craters. It turns out because there's no atmosphere on the moon and no weather, any of the craters that occur there from being hit by meteorites and such stay for pretty much ever because there's no wind, no water, no air to wear those down. At first, scientists did not know if they were volcanic craters or impact craters, and it turns out they're mostly impact craters. Yes? Yes. All right, so the question is, if you throw a, a rock into the surface of the moon, will it make a really awesome crater? You know what? I believe it'd be kind of similar to taking a nice large ball bearing or a piece of gravel and throwing it into a thing of flour, right? Baking flour, and so it'd be poof, it'd make a nice. And best of all, it would stay there, and then you could come back home from the moon, and nobody's been there since the 1970s. I'm not sure how you got there, but yes, your crater would still be there. The footprints from the Apollo missions are still there. Anyways, the moon is about 30 Earths away, which is kind of a strange measure, but 30 Earth diameters. The moon has a very similar geology to the Earth. And this gives us great clues about how the moon was formed. Our moon, Earth's moon, as you saw in the video, is very different from the other moons in the solar system. The other moons in the solar system, many of them are captured asteroids. They're very small compared to the size of the planet. Our moon is very big compared to the size of our planet. We know from the Apollo missions that it's very similar geology. A lot of igneous rock, a lot of rocks we could identify. There are moon rocks that were brought back in the Apollo missions that scientists are still studying. And because there's no atmosphere, the temperatures range from 130 degrees Celsius, remembering that water boils at 100 degrees, down to negative 180 degrees Celsius. So that's pretty cold. And those extreme temperatures, you get that extreme temperature to some extent even going from sunlight to shadow. Our atmosphere causes a greenhouse effect, which acts as a blanket, which tempers the temperatures. It makes them less extreme. So very hot, very cold. Yes. Okay. We shall save that for when we talk about the solar system next week. Okay, so this is all basic facts about the moon that you probably read about and that you'll probably see on the quiz. In terms of our solar system, and in 2 or 3 weeks when we start talking about the solar system, not all planets have moons. The inner planets do not have moons. So Mercury and Venus do not have moons. No moons. Mars has 2 small moons that appear to be captured asteroids, which is odd because it is a smaller planet than us. So these odd potato-shaped, not spherical moons. And because it doesn't have a big moon, there's much more wobble on the atmosphere, on the axis, and so really wild, unpredictable seasons. The gas giants, Jupiter, Saturn, Uranus, and Neptune, have lots of moons, 50, 60, 70 moons. Most of those moons are small captured asteroids, but they each have, 4 or 5 or 6 large round moons similar to the size of Earth's moons, and tons of little bitty ones. But again, in a couple weeks, we'll talk about that as we talk about the solar system. So, formation of the moon. And through much, there used to be like 3 or 4 hypotheses of how our moon got there. And this is now the generally accepted theory of how the moon formed. And so first of all, this we know that the rocks on the moon are both of a similar type, but a similar age. Remember, we can do absolute dating, radioactive dating, to come up with the age of igneous rocks. So the Earth formed about 4.6 billion years ago. Approximately 4 billion years ago, scientists believe there was a collision with an enormous asteroid of some sort. And I believe, huge. So like moon-sized or Mars-sized thing crashes into the young Earth, which is, there's still, so 4 billion years ago, the earliest life is like 3.5 billion years ago. So huge explosion. Because things are spinning, so a huge chunk, all this stuff is just blown out into space. But because of gravity, remember universal gravitation, every mass attracts every other mass, the stuff that's kind of floating out here in orbit kind of conglomerates together and becomes, and it's molten enough that it becomes very spherical. And the rest of it either gets absorbed or falls to Earth as asteroids. The Earth is all kind of remelted there, and because it's still spinning, becomes a sphere again. And so then we end up with our one beautiful, huge moon. And again, it seems in some ways fantastic, but the 2 major lines of evidence is we know for a fact that the rocks on the moon are a similar type of rock and a similar age. And so that supports this idea that if this all happened, the moon is made of the same material as the Earth, because whatever the moon was became part of the Earth, and the Earth became part of the moon. And this happened, and then as it cooled, once the rocks melt, the age you're measuring is from when the rock cooled. So those are the 2 major lines of evidence that support that. The captured asteroid theory and other things wouldn't follow this evidence. Yes? In past years, I've spent a little time talking about the Apollo missions, simply because a lot of times people don't really fully understand a lot of the details. One of the most interesting things that I have found as I teach students, many people don't realize the only human beings who have ever been on the surface of the moon are American males. And that's not that that's sexist, it is that back in the 60s, when they were training for this program, they took primarily military fighter pilots, which were all men. And so those were the ones. The Russians at the same time had, this is called the space race, and there was a race, a political race, and yeah, so it was a race to put the first human in orbit, a race to put a man on the moon, and Russia, the Soviet Union, won many of the stages in this race. Russia had the first satellite, Sputnik. Russia put the first human in orbit. The human astronauts were called cosmonauts. But then, when the United States put the first man on the moon, it kind of ended the space race and we won. But I think there's a lot of interesting things. Russia and the United States have very different space programs, even at this time. And in fact, um, one of the things that the Americans did then and still do now to a large extent is safety and backups to the backups and, you know, triple failures. And so there were many and much more protection of the astronauts. And so on one way, that makes it much more expensive and slower, but we did end up being the first ones here. So a brief summary. Apollo 1 was an accident on the launch pad. If you have, there's two really good kind of historical fiction biographical things that you can watch. One of them is, of course, the movie Apollo 13, which is historical fiction but mostly true. There's another one. It is I don't remember which channel. It's called From the Earth to the Moon, and it's a miniseries. And this one is really good. And this is because it's a miniseries. It's much more in depth. It's very similar to Apollo 13. It's very engaging to watch and very historical. So Apollo 1 was an accident on the launch pad. When they first were designing this, they had 100% oxygen atmosphere in a pressurized cabin. And what happened was, part of what was going on is there was such a push to engineer things that not everybody was listening to everybody else. And what happened, there was one small spark, and these three men, and this was just a practice run. It wasn't a live launch or anything. And these three men very quickly burned, suffocated, died. They couldn't open the escape hatch because of the way the positive pressure was. The escape hatch opened in, and the pressure was pushing it. So they kind of had no chance, which is absolutely tragic. But with this, then they totally revamped the design. And again, if you watch From the Earth to the Moon, very good. These are some of the other ones. Then, of course, Apollo 13, the mission was aborted. They came back. They didn't go to the moon. You still have to, you can't just defy gravity, right? So they still had to go around the moon and come back without landing. Yeah, there was a failure there. The last time that humans were on the moon was in December 1972 with Apollo 17. So check it out, and we will do our lab tomorrow.